Good evening, students. Today, I'll take you people into the concept of memory. Okay. So, but before that, I would like to know what we discussed in the previous session. If you could tell me, I will, explain a few great questions. After which, I will go to uh, the next topic, that is memory. Now, okay, fine. As I'm not getting any answers here. Is first of all, is anybody there out? If you could say yes, I will take it from there. Yeah, yeah, fine. Today, let us start the concept memory without wasting any time at all. Okay. Yeah, now let us start memory without wasting any more time at all. Today, there we go conceptual wise, concepts wise. I will let us I will give you some overview of the entire memory hierarchy, and I'm going to explain you guys how important is the memory for an entire computer system, for an entire what we call you know the CPU structure, how memory acts as a backbone. Okay, for that let us get into the details. Yeah. Now, first, when we talk about the memory, let me tell you that we always will talk about main memory. What do you mean by main memory? And what is the difference between the other memory devices that are connected to the system? Let us get into the details. Okay, first let us discuss about memory hierarchy, because memory hierarchy, if you can understand, then getting into the details of the memory will be quite easier. Okay, first of all, let us start from why do we require memory, and what is the purpose of using a memory unit for the system, and how this memory unit acts as a backbone. Let us see. Okay, yeah, you know that the CPU executes the programs, right? CPU executes programs. Okay, all these programs are needed to be stored somewhere, that is main memory. Okay, when we discussed about the CPU architecture, we discussed something about stored program organization. What is stored program organization? Store program organization is a thing which is also known as one Neumann architecture. One Neumann architecture. It is not writing clearly. One Neumann architecture. What is one Neumann architecture or store program organization is all about? Simple rule of the store program organization is when a programmer executes a program, the basic rule to execute the program is first, that program must be stored in the main memory. This is the fundamental rule. If a programmer needs to execute a program, that program must be stored in the main memory. Unless there is no way the program can be executed. So this is a simple and fundamental rule of a computer system. This is the reason why we do require a memory unit. Okay, so memory unit essentially stores all the programs. The programs what do we have that are needed to be executed by the CPU concurrently will be residing in the main memory. Let us say this is called main memory. Okay, now using this main memory as a backbone of the total memory system of a CPU, let us discuss the total memory hierarchy of the computer system. In the memory hierarchy, the first thing that is going to stand is the CPU itself. Okay, CPU is the first component to be standing in front of any other thing in the entire computer system, because CPU also has a memory logic. CPU also has a memory logic. What is this memory logic of the CPU? The memory logic of the CPU is in terms of the registers. CPU has registers. Okay, because the computer system all the time stores the programs in the main memory, but the CPU executes the program one by one. And when a program is getting executed, at a time CPU cannot execute the total program. Rather, it executes the program taking the instructions one by one. So what the CPU does all the time is fetching the instructions one by one. When an instruction gets into the CPU, it requires a storage area. Okay, that storage area is available in terms of the processor's registers. Okay, if you want to have a complete idea about the register set, just access my previous classes on the registers, so you could have a vast idea about the register set. Okay, so CPU, as it also has a memory logic, CPU stands first in the total memory hierarchy. Okay, Lokesh Pranab, yeah, hi, yeah, what you want me to repeat? What you want me to repeat? I didn't catch you, Lokesh. Lokesh, are you there? Lokesh, listen. Today, I will explain you guys. Okay, from the starting, there is nothing I started. In fact, I have been explaining you guys about the memory hierarchy. That's it. We are done with the CPU, right? In CPU, we did everything. We finished most of the gate questions also, right? Okay, last week you didn't attend. Fine. Anyhow, we finished CPU. Now we need to start memory. In order to start with memory, the first thing that we need to discuss is the memory hierarchy. What is memory hierarchy? Various components that are organized in a structural pattern in the CPU. This is called a memory hierarchy. What is the order of the memory components that are arranged in the CPU? Okay, so the first thing that stands in the total memory hierarchy is the CPU itself, because CPU also has a memory logic. Many times I told you guys in my CPU organization, because you people know what is a register structure, right? What is a register organization? Why do we need registers? The registers are badly needed by the CPU Because when the CPU executes the instructions, CPU has to store the instructions and the associated data in the local storage provisions. These local storage provisions are provided by the architect in terms of the register set. Alright. So CPU stands first in the total entire memory hierarchy. This is what the CPU is all about. Okay, in the memory hierarchy, how it starts. Okay, now as this is the CPU, whenever CPU wants the data, it is going to get it. It is going to collect it from the main memory every time. Either it is an instruction or data. Okay, either it is an instruction or data. Every time when CPU requires a data element, it will collect it from the main memory. So these are the two basic things in the memory hierarchy. Of course, we do also talk about something called secondary memory here. What is secondary memory? Try to understand. You may have a huge number of programs that are not needed to be executed all the time. Okay, first of all, you know the concept of the program very well because you've been following the classes very carefully and regularly. What is a program? Everything is a program. You watch a movie, you listen to a song, you execute a Java program, you move a mouse. Everything is just nothing but a program, right? Now, let us say that you do have 1 terabyte of programs. But do you execute all these programs at a time? No. You don't need to execute. You don't execute all these programs at a time. But still you have to store all those programs in a in a dump yard, whatever we call. Okay, so this dump yard is called secondary memory. Okay, this secondary memory nowadays we are using, okay, in terms of optical hard disks, that is in size of 1 TB or 2 TB or whatever. So secondary memory will act as a storage yard. All the programs that are available at the user will be stored initially in the secondary memory. Now, whenever the user wants to execute the programs, all those programs will get transferred from secondary memory to the main memory. That means that main memory will have those programs that are executed concurrently, that are getting executed concurrently. Okay, so all those programs which are getting executed right now will get stored into the main memory. Of course, CPU will pick up a program. That program will be selected from one of those programs that are available in the main memory. Again, there is an operating system concept. A scheduler will come into the picture and will schedule one of the programs based on some scheduling criteria. Once after the CPU decides to execute a program, then the CPU will start fetching those instructions of the program one by one. All those instructions will be transferred to the CPU one by one. As they execute, finally the program will get finished. So this is the initial memory hierarchy to start with. You got me? Okay, so this is the initial memory hierarchy. But here try to understand. You can see that CPU always talks to the main memory. CPU can never talk to the secondary memory. CPU, for an example, when CPU doesn't have an information in the main memory, it don't go to the secondary memory. Okay, the information that is needed by the CPU, first of all, will get transferred from secondary memory to the main memory, and eventually CPU will have to access it and collect it from only the main memory, only from the main memory. Okay, so CPU will never talk to the secondary memory directly. This is the initial and fundamental and a very important thing that is needed to be understood by you guys. Okay, how important is the main memory? Since the CPU can no way communicate directly with the secondary memory, okay, you can understand the essence of the main memory here. You got me? This is the thing. Now, you also knew something about the cache memory. You also knew that in the main memory hierarchy, there is a small but an efficient memory which is called a cache memory. You might have heard about the cache memory, didn't you? You know about a cache memory, right? What is this cache? Could you please answer me why we do need a cache memory? Could you please let me know what is this cache memory? Rather, I'll pose the question in a different way. What do you know about cache memory? Simple. Okay. I don't want you to get into the complete details of the cache memory and explain me. Okay. So what you do is, what you know about the cache memory, just type. Okay. Anything which you feel that needed to be posted here. You just tell me, what do you know about cache memory? Lokesh. Should I wait or should I continue? Or you want me to explain what is cache memory? Yeah, fine. Anyhow, let me tell you what is a cache memory. When I ask you guys what is a cache memory, you people may tell me that cache memory is the what do you call repeat rest. Cache memory is going to store the repeatedly accessed information. The information which is stored in the cache can get accessed faster, and many other things, right? You people may tell me some of the important features of the cache memory, but the fundamental question, if you can understand, you won't go for the features. My question is, anyhow, I told you guys that the programs are residing in the main memory. Okay, the only memory that will be considered substantial for the CPU is the main memory. As far as the CPU is concerned, there is no other memory to substitute main memory. Main memory can never be substituted by any other memory. Okay, main memory is always main memory. He is the ultimate the storage unit for the CPU. Every time when the CPU wants an information, initially and finally will get collected from the CPU. Okay, yeah. Now let me tell you why cache is important. Why cache is seriously important. Let us talk about the CPU. Before we get into the details of the cache memory, let us talk about the CPU. How CPU, on which rate CPU is going to access the information, rather performs the tasks. I will tell you. CPU performance will be measured in hertz, right? CPU performance or speed. Let us say the speed of the CPU, rather whatever you call the performance of the CPU will be measured in terms of gigahertz. Okay, yeah. The previous access from the main memory is loaded in the cache memory. This may increase the performance. Okay, fine. Just hold on for now. You are going to understand the complete thing about the cache memory after this class. Okay, stay focused and understand it carefully. CPU speed will get measured in gigahertz, right? Let us consider a processor with 1 gigahertz speed. I do have a processor, that is Anil's processor. I have designed a processor. I named this processor as Anil's processor. Okay, so this Anil's processor is of 1 gigahertz speed. Fine. Okay, of course, you can ask me, sir, nowadays we are talking about 2.8 gigahertz or 3 gigahertz or 4.6 gigahertz. So fine, my processor is the oldest processor for now. You consider that my architectural skills are way behind, but fine. Let us consider Anil has a processor. Anil designed a processor with 1 gigahertz speed. What is this 1 gigahertz? This 1 gigahertz means that this processor can work at a rate of 10 power 9. 10 power 9. What is 10 power 9? 10 power 9 meaning after 1 there will be 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What is 1 gigahertz? 1 gigahertz means our clock is based on 1 second. Human being's clock is based on 1 second. This 1 second will get divided into these many clock cycles. Okay, these many pieces. 1 second has been divided into these many pieces or clock cycle, whatever you call. Okay, So which means that see, I'll put it in a different way. If you want to perform a task, the smallest amount of time that you require is 1 second. Okay, but when it comes to the computer system, it depends on the clock speed. If the clock speed is 1 gigahertz, okay, and it requires 10 power minus 9 seconds. It is a 1 nanosecond. 10 power minus 9 is 1 nanosecond. If at all CPU has to perform a task, the minimum time quantum that it requires is 1 nanosecond for a 1 gigahertz processor. So, which means that CPU will be able to perform 10 power 9 tasks for 1 second, right? Did you understand? Exactly. 10 power 9 cycles in a second. So, CPU will be able to perform 10 power 9 tasks. The number of tasks that are performed by the CPU is 10 power 9, 1 second. Okay. So, here, I do have to put something here. Now, what is the main task of the CPU? The only task of the CPU is executing the instruction, right? Of course, there are a lot of, this is at a very basic level. We are assuming, okay, and in order to get the things clear, we are asserting certain facts. But when we look into the actual facts, these facts will have to be discussed even more clearly. But at this stage, we will assume something, imagine something, okay, to understand the principle why we implemented cache memory. A 1 gigahertz processor is going to work on a rate 10 power minus 9. That means that the CPU will be able to perform the tasks which are equal to 10 power 9 a second. Okay. So what is a task for a CPU? Task is for a CPU is executing an instruction, right? CPU always is going to execute the instruction. That's it. Other than that, the CPU has got nothing. CPU has got nothing to do with any other thing. CPU always executes the instruction, which means that CPU is capable of executing 10 power 9 instructions 1 second. Instructions per second. This is the speed of the CPU. Okay. The actual speed of the current CPU is 10 power 9 instructions per second. Why 10 power 9 instructions per second? Because CPU is 1 gigahertz. 1 gigahertz is equal to 10 power 9. So CPU will be able to perform 10 power 9 tasks per second. What is the task of the CPU? Task of the CPU is just nothing but executing an instruction. Got me? So CPU is capable of executing 10 power 9 instructions per second. Hold on. Here I do have to put something. That is, okay, fine. CPU is capable of executing 10 power 9 instructions per second provided somebody gives these 10 power 9 instructions per second. You understand? I am so fast. I am the CPU. My rate is 10 power 9 instructions per second. But there has to be a supplier who can reciprocate to my rate. That is, somebody should give me 10 power 9 instructions per second. Then only I'll be able to execute. Okay. So it is clearly based on my supplier. If my supplier is capable of feeding me 10 power 9 instructions per second, then I will execute. But if my supplier says that no, I can't supply you 10 power 9 instructions per second, then my speed will be limited by my supplier. Obviously, the eventually total speed of the system will be limited by the supplier. Here my supplier is very poor. Why? CPU is the fastest device. There is no other device can be compared with the CPU. CPU is the fastest device. But who is going to supply this 10 power 9 instructions per second to the CPU? That is our main memory. Main memory has to supply the instructions at the rate CPU is asking. But the main memory is not as fast as the CPU. Main memory is very, very slow comparing to CPU. Main memory is very slow because CPU has to access main memory and to locate a particular specific address in the main memory, it takes a lot of time. So eventually the total speed of the system will be limited by the memory speed, main memory speed. Let us say that the main memory will be able to supply only 1 lakh instructions per second. So here, no matter how faster is the CPU, eventually the total system speed is limited by the main memory speed, right? Okay. So here you boast as much as you want about the CPU, doesn't matter. Finally, your system speed will be limited by the memory speed. You got my point? So this is the reason why what do is we will involve a small but faster but efficient cache memory in between the levels of the CPU and the main memory. Okay, you can understand that. Now already you got it that CPU is the fastest device, but the main memory is not as fast as the CPU. So the total system speed is primarily getting limited by the memory speed. So in order to overcome this, what we do is we will involve a small but faster memory in between the levels of the CPU and the main memory to compensate the speed differences between main memory and the CPU. Okay, this is the reason why we involved cache. We are using a cache. Why the cache is being used? Cache is being used to compensate the speed differences between CPU and the main memory. Nothing else. In order to compensate the speed differences between CPU and the main memory, we use a cache. That's it. There is no other, reason why we use a cache. But we talk about many other things about the cache. That is, you may tell me that repeatedly accessed information will be stored into the cache memory, in the cache memory. Yeah, I do agree with you. But that is not the purpose why we implemented cache. That's the feature. That's the feature of the cache memory. That's the characteristic of the cache memory. That is an attribute of the cache memory. Okay, but the reason, but the motto why we use a cache memory is entirely different. Okay, so this is what a cache memory. Then you talk about anything else right later. Okay, so then you talk about repeatedly accessed information. Repeatedly accessed information. Faster memory, etc. Okay, but these are all just characteristics or attributes or whatever you call, which are observed after you implement something, after you involve something. When you observe the performance, these are identified and observed. Cache memory is storing the repeatedly accessed information. That's it. Just an observation that is made out of the cache memory. I hope you got my point. Okay. Yeah. Of course, as you love, as you told me that I love the cache concept. Of course, continue this obsession with the cache memory, because this cache memory holds the utmost importance in the entire memory hierarchy, because most of the questions, when you observe the previous years, are from the cache memory. Okay, there are several concepts. When you talk about memory, 80% of the topics will definitely fall into only the cache memory. Cache memory is such a huge concept. Just following my classes, I am going to make it very simple and clear. Okay, there might be several ambiguities and confusions when you guys go through the books and look into those details. But let me tell you something. That is, henceforth follow my sessions carefully. I am going to make it very simple and clear. As simple as this. Okay. Oh, this request must be posed to the Ekeeda people. Of course, they do have a playlist. I think they do have a playlist. This request must be posed to the Ekeeda people. I don't do such stuff. I just take the classes, and because time is very precise, so you just can ask them. Okay, these Ekeeda people. If you do have mail ID. You just can talk to them, and they will definitely create a playlist. Okay. Now let us get into the main memory design. We design the memory. Okay. What is memory? What is memory? Memory is just, as I told you, for a CPU there is only one memory, which is called rather main memory. I hope you got it. There is only one memory for a CPU, that is main memory. Other than that, a CPU doesn't say anything. If you ask CPU what is the only memory that you have, she says all the time that my main memory is my total memory. Other than that, I got no memory. You can ask me, sir, what is cache memory? Cache memory is not a distinct part of the main memory. In the total main memory hierarchy, cache memory is an integral part. Okay, I'll put it this way. If you have a main memory which is of a size 1 GB and cache memory which is of a size 500 MB, your total main memory size is still 1 GB, because this 500 MB contains the same information, rather the replicas of the information which is available in the main memory. Okay, so the only memory that CPU possesses is just the main memory. Other than that, CPU doesn't have nothing. Okay, now we will design main memory. Okay, so here we will see what is main memory. When you talk about main memory, you talk about RAM and you talk about ROM. Okay, what we do is we will design both RAM and ROM chips. Okay, we will try designing RAM and ROM chips. What is RAM? RAM is just nothing but random access memory, right? What do you mean by random access? Once again, I will show you what is random access. Okay, stay focused here. Let us say my memory is of, let us say, 4096 words. We design a memory unit with a 4096 words. Okay, in which the first address is the 0th address, the final address is the 4095th address. When CPU wants to access some information, it will send an address. Let us say CPU wants to read an information which is a 23rd address. Are you getting it? CPU, let us say, at this instance, want to read information which is available at a 23rd address. So this 23rd address will be transferred to the address bus. You know, I talked already about the bus system. You don't ask me what is the bus system. Bus system is a transportation medium between CPU and the main memory. Okay. Initially, the address will be put into the address register. Then from the address register to the address bus, it will get transferred. Any doubts here, Lokesh? Yeah, good. Now, from the address bus, when the address has been transferred into the address bus, this address bus will take this argument of 23 to main memory. Okay. Now, after which, this address will be compared with the addresses that are available at the main memory randomly. You don't go for a sequential search. 0, 1, 2, 3 like that. Just it goes for a random search. Okay. In the random search, some address references will be compared to 23 randomly. Okay. And finally, we will come to the exact location 23. Did you understand this location? This address reference 23, which is required by the CPU, will be compared with some addresses randomly at the main memory. And finally, it locates 23 and it is going to read the information. Initially, it may locate 423. As 423 is not equal to 23, it goes to another address, that is 512. As it is not equal to 23, it goes to 9. As it is not equal to 23, finally it just go to 23. Finally, it just 23 has got located. Then once after the address has been perfectly matched, then the information will be read by the CPU. This is how random access does work. When you talk about ROM, don't think that ROM is sequential access. ROM is also random access. Did you understand this? This is an important thing. Okay. This is an important thing to understand. ROM is also random access. But why we do call it as a ROM? ROM we use this term because in ROM you can store nothing. Rather, you cannot write anything into the ROM. Once after you design a ROM, some programs will be transferred to ROM initially before you design the computer system itself. Being a designer, you must choose those programs that are needed to be put into the ROM. Okay, then you just then burn this RAM, burn this ROM. Burn meaning you don't put petrol and burn it. Okay, burn meaning that being a computer science guy, you burn ROM with the sufficient number of the programs are the required programs that are needed to be accessed when computer system wants. So ROM, when you access it, it only gives you the information. It doesn't accept any more information once after it is completely designed. This is the difference between RAM and ROM. How the information is accessed, both are one and the same. RAM and ROM both are random access. Did you understand this? Good. Good. Now, let us talk about design of the RAM. Okay, you might have heard about static RAM and dynamic RAM, didn't you? You might have heard about static RAM and dynamic RAM, right? Do you know about static and dynamic RAMs? Can you tell me yes sir, no? Make it fast. Yeah, good. When you talk about a static RAM, static RAM based on is based on the power supply. As long as the power is applied, RAM works. The information in the RAM is at your disposal as it is there for taking. The moment you lose the power, the information is gone. This is static RAM. Because static RAM is designed by using semiconductors. There are several semiconductor materials, germanium, silicon or antimony, whatever you call. But all these semiconductors based on power supply. As long as the power is applied, RAM works. The moment you lose the power, RAM vanishes. But when it comes to the dynamic RAM is based on capacitor technology. How capacitor technology works? Capacitor technology is based on getting charged and discharged. Once after all the capacitors are fully charged, then the RAM is, the information in the RAM is at your disposal, is available for taking. But the moment the capacitors completely got discharged, information is gone. So here it is somewhat prominent than static RAM, right? Because it is just not depending on the power. It depends on how quickly, how lately the capacitors are going to get discharged. This is what the dynamic RAM. So dynamic RAMs are more costly than the static RAMs because capacitors are more costly than the static RAM semiconductor materials. But these are prominent. The information will be sustaining more longer than the static RAM. And designers have approached one more way to have the information sustained in a dynamic RAM. How? What they do is simple. I will tell you one important fundamental rule to have your RAM all the time activated even without the power. Once after you switch on your laptop, whether desktop or whatever, even though you're not executing any programs, even though your CPU is at a idle or your sleep state, there will be some accesses sent to the RAM. Okay, dummy accesses. RAM will be accessed for every now and then. Okay, some dummy references will be sent to RAM in order to just keep this RAM active. Did you understand this? Any doubts you ask me, I will tell you right now. In order to keep this RAM active for more longer, even though when a programmer is not using the system, some dummy references will be sent to the RAM. Okay, as long as RAM is engaged, then this RAM is completely working. All the capacitors are completely charged. The moment you stop talking to the RAM will get started discharging. So in order to avoid that, this RAM will always be contacted. Either you execute a program or not. As long as you execute the programs, anyhow you execute, you access the information, instructions and the data all the time. But the moment you stop working the system, the CPU itself, it takes care of how to engage the RAM. It always will send the dummy references. As long as the dummy references will be sent, RAM is always engaged and occupied. Okay, so this is how RAM works. Okay, now let us get into the details how RAM is designed. How RAM is designed. Okay, let us say this is the RAM. When you have a look at a RAM, if we can have a look at the RAM will have these many connections. There are a total of 5 connections you can see. Here, there is something called CS1, CS2, read, write, address, data. Okay, and you already know what is read and write. When read is enabled, the data will be transferred to the CPU. When write is enabled, from the CPU to the RAM, the data will get transferred. So this is just all about read and write. So this address bus, you know already what is an address bus. There is an address bus. System uses an address bus. When CPU sends an address through the address bus, the address bus loads the address into this address lines of the RAM. The moment address lines are loaded with the address, immediately the address will get located in the RAM, within the RAM. Okay. After which RAM checks for either read or write. Which of these, the inputs are actually enabled. RAM switches for the enabling of one of these inputs. When one of these inputs are enabled, then appropriate operation will get performed. Let us say read is performed. Then address is located. Under the address, the data will get transferred to the data bus. From the data bus to the CPU. Read operation, meaning from the RAM to CPU. When write is performed, when write is enabled, address in the address lines will get located in the RAM. Then the data in the data lines will get transferred to that specific address. This is just nothing but the read and write operations, how they are performed. Now you can ask me, sir, what is this CS1 and CS2? Anyhow, we know everything about read and write. How read and write does work and address and data lines does work. Fine. When you talk about CS1 and CS2, first of all, you have to understand the thing about how the memory is actually going to be designed. Okay, and there is a concept called distributed memory. Or memory interleaving. Distributed memory or memory interleaving. Okay, so let me let me explain you guys about what is memory interleaving. Let us say that in my computer system I am using 1 GB memory. My main memory is of a capacity which is equal to 1 GB. Okay, I do have a question. When your computer system started giving trouble, it is troubling you. Which is the first suspect in the entire system? Obviously the memory, right? Okay, because when if the computer system is not working, the main culprit will be the memory itself. You got my point? Okay, let us say your computer system failed to boot. Which you are going to suspect? Main memory only, obviously, because it is the basic component that can get damaged every time. Okay, that can get damaged all the time. Because only there are two components always occupied. One is CPU and one more is main memory. These are always occupied. As long as CPU does work, memory also works. Okay, both works, complementing each other, in conjunction with each other. But CPU is a stronger guy. But main memory is not as stronger as the CPU. What is the difference? For this, I don't need to explain you Pythagoras theorem, or I don't need to turn the world upside down. I'll ask you simply one thing. Just take CPU in one hand. Just take your memory chip in other hand. Okay. Just feel. Obviously, you can tell me that the CPU is more stronger and solid than the memory, right? But here, these two people are working in conjunction all the time. Obviously, memory will today or tomorrow will definitely fail because CPU is very stronger. Many protection mechanisms are enabled and associated with the CPU. But when it comes to the memory, main memory is a weaker guy. He's a cripple. Okay, obviously this cripple will lose, his life sooner or later. I hope you got me. Okay, here the thing is, when I use 1 GB memory, when I design my main memory, what I do is, of course, I foresee this problem, and in order to have this memory sustained for more longer, what I will do is, I don't design this memory with 1 GB chip. I don't design this memory as 1 GB chip. My total requirement is 1 GB. Now what I will do here is, I will use 4 different chips of equal size rather than using one single chip. Obviously, I don't use one chip. Rather, I will divide this 1 GB into different chips. Rather, equal sized chips. 256, 256, 256, 256 MB each, which collectively gives me a total of 1 GB capacity. Okay, so here the burden is distributed equally. The burden is equally distributed among all these chips, isn't it? So here, of course, the memory will sustain for more longer than using a single chip. Of course, you got my point very clearly. This is called a memory interleave. Okay, now these CS1 and CS2 will come into the picture. When the CPU wants to talk to one of these chips, that means that when one of these chips are needed to be selected, CPU uses this CS1 and CS2. I hope you got it. Okay, all these memory chips would have these connections, CS1 and CS2. Okay, and CPU will use a combination of 1 and 0 to select one of these chips, which means that for a specific chip, CS1 and CS2 combinations will be 1 and 0. For all the remaining chips, the combination will not be 1 and 0, which means that only that specific chip is selected to communicate. Remaining all the chips are not selected at that time, so they are not accessed at that particular specific time. Did you understand this? Once again, whenever CPU wants to communicate with one of those chips, it uses this CS1 and CS2. CS1 and CS2 are actually called as chip selector 1, chip selector 2. Okay, because there are 4 memory chips. CPU has to select only one chip, either for reading or for writing. Okay, only CPU can communicate with one chip at a time. So what it does is, it uses a combination of 1 and 0. Okay, if I want to select the third chip CS1 will be 1, CS2 will be equal to 0. Then third chip will get selected. What about the remaining chip? Remaining chip combinations, the remaining chip, CS1 and CS2 combinations will not be equal to 1 and 0. So CPU ensures to select only one specific chip by enabling a combination of CS1 and CS2 which are equal to 1 and 0. Did I make it myself clear, Lokesh? I hope I did. Okay, so this is what all about, CS1 and CS2. That's the reason why you can see that for CS2, I put a bar. For CS2, I put a bar. Did you see the bar there? Which means that when CS1 is equal to 1, CS2 must be equal to 0 to enable this specific chip. When one specific chip is enabled, none of the other chips are ensured that those are not enabled. Because CS1 and CS2 will not be 1 and 0. Okay, that also I'll explain. How CPU ensures that only one specific chip CS1 is equal to 1 and CS2 is equal to 0, and the rest of the other chips CS1 and CS2 chip selector combinations will be different. I will also explain in my upcoming sessions. Okay, so this is all about designing RAM. Now let us design ROM. I'll put it this way. What is the difference between RAM and ROM? Let me tell you that ROM is also designed in a similar fashion to RAM. But when it comes to ROM, I don't need a few connections in the RAM. That's it. If I can avoid a few connections in the RAM, then ROM is designed. Which are the connections are not needed for a ROM? If you could tell me, I will go ahead in designing ROM. Just have a look at the RAM. Which are the connections you feel that are not necessary or are not needed for ROM? If you could let me know, then we will go ahead in designing ROM. Write is not needed, right? Okay, stay focused. I expected this answer. Of course, anybody would tell me that write is obviously not required. Any doubts about that? Let us talk. I will talk to you, just talk to me. As far as your knowledge is concerned, write is not required. I do have a question. That is, do we have read even? Do we require read connection for a RAM chip? Sorry, for a ROM chip. For a ROM chip, do we require a read connection even? Anyhow, write is out of case. Because even if you enable write, nothing will happen. So obviously, a designer wouldn't go for a write pin. Write pin will be discarded. Got me? So, my question is, do you even require read connection? Just tell me. Think carefully and tell me. It's not a rocket science, it's just about a discussion. As long as you participate more and good, you're going to master your subject. First you think about how to master your subject, then you talk about any exam. There is no such level called as gate level. Okay, there is only subject level. If you could masterize the subject, then any exam you can attend. Simple. All the exams will be simpler, isn't it? Lokeshwara, you think we require? Hold on. I will make it, make your assumptions clear. Very, very, very easy. When there is a unit which is only intended to do a specific purpose, which is only intended to be used only for a specific purpose, again, do you say that you need to do this? Understand my question? There is a unit. That unit is doing only one specific purpose. That unit is serving for only one specific purpose. Okay. If the unit is serving for two purposes, I will put two switches. When you switch on one, then the unit will be acting for that purpose. When you switch on the second one, then the unit will be, serving for other specific purpose. Now, there is a unit which is intended to serve for only a specific purpose. My question is here, at least do we require that specific switch, one specific switch? No, we don't require. I'll put it this way now. Did you understand? I hope you got it. I don't need to explain you. Should I? When you touch ROM, it doesn't do any other thing rather than reading. Should you require even a read connection? It's not required. Yeah. Good. That's it. Other than that, I don't have any explanation. Simple. It is just common sense and common perception. Right? So here, tell me what are the connections? Just CS1, CS2, address, data. CS1, CS2, address, data. That's it. Okay. So this is all about designing your memory chips. Now here, how much time we got? Just over, right? But fine. Nevertheless, we had a productive discussion this week. Once after we have our fundamentals right, stronger, then it will be laying the stronger foundation for the complex topics that we are going to discuss in the later upcoming sessions. Next session, remind you, is one of the important sessions in the entire computer architecture. Next week is very important. Don't miss that. Even there is another person who regularly attends my classes, but nowadays I'm missing that person. You just remind that boy or girl. Next session, we will get into the details of cache memory. If you can, actually follow the next session, let me guarantee you that if 4 questions are given out of computer architecture, 2 questions you would definitely be able to solve. As simple as this. Okay. So, what you do is, before coming to the next session, I do have some things to ask you guys. Anyhow, you people knew about cache memory, right? I'm going to give you a task. That is, just go through something called the design of the cache memory. That is, what is locality of reference? There are 2 things in the locality of reference. If you could brush this locality of reference concept and come for the next week, the things would be relatively simple. Okay, anyhow, I'll just request you guys to go through this concept of locality of reference. Definitely, you won't get as simple as this. Simple. The thing is, you read as much as you want. But I will show the other dimension of locality of reference. You access any number of books. Carl Hammack or Computer System Architecture by Maurice Mann. You go through as many books as you want. You will have a basic idea, but not a complete idea. Let me tell you. Then the moment you come to the next class, I will give you the actual dimension of this cache memory. You will definitely be wondered. Let me give you an assurance that at the end of the next class, no matter which question you're expecting out of the GATE exam, you will be confident enough to solve whatever it might be. I hope you got me. Okay, so that's it for today. And when you come for the next class, do what I said. That's it. But if you come without doing what I asked you for, then both dimensions I need to explain, because simple cache memory is the very simplest thing. At least the basics of the cache memory, 1 or 2 points. If you go through them, it will give you some idea. Basics, if we discuss in this doubt session, I don't see the feasibility. Fine. Forget bygones are bygones. What you do is just go through the locality of reference concept. Go through Google, Carl Hammack, Computer System Architecture, वगैरह, etc. But come back next week, or even you have my mail ID. Just mail me what is locality of reference in your own words. I don't want this copy pasting this thing. Already you participated in one of my previous questionnaire. Yes or no? When I pose a question, you answered me. You are the only guy who answered me. And fine. That is it from my side. That's it. In one way, I was thinking the same. Fine. So that's it for this session. And we're going to meet next week. Same day, same time. Okay. Thank you so much.